Okay, in this video we're going to go over some of the different types of problems that you have in your acid-base packet. We're actually going to start off with the buffer page. So remember, in order to have a buffer, you need to have two things, right? A buffer consists of a weak acid or a weak base and its conjugate. Right, so we need to figure out if these solutions as given will have these two components in it. Right, so if we look at solution number 1, we have 1 molar sodium chloride and 1 molar hydrochloric acid, equal volumes. The number of moles will become very important for some of these types of problems, especially when we start doing some of our little sneaky buffer. Right, so if we look at this, we have hydrochloric acid as our acid, and we have the conjugate base of hydrochloric acid. So we have an acid and we have its conjugate. The problem is that HCl, hydrochloric acid, is not a weak acid, it's a strong acid. So because it's a strong acid, this is not a buffer, so no buffer. For number 2, HAC. AC is usually how I'm going to abbreviate acetate, so HAC is acetic acid. We have a solution of acetic acid and a solution of sodium acetate. Acetic acid is a weak acid, so that's one of our two components, and the acetate ion is its conjugate base. So we have both components required, a weak acid and its conjugate base, so this is going to be a buffer. Now we have hydrofluoric acid and sodium hydroxide. Hydrofluoric acid is a weak acid, so we have that as a component. Sodium hydroxide is a strong base. Now this would lead you to believe that we don't have a buffer. However, the thing that you have to remember is that when HF comes in contact with the hydroxide ion, we're going to form F- and water. Right, so if we add hydroxide, we actually wind up forming the conjugate base of hydrofluoric acid. Now, because we didn't add enough sodium hydroxide to completely react out the HF, we're going to have some amount of HF left over, and we're going to create a little bit of fluoride ion. So this is, again, one of our sneaky buffers. We have a weak acid or base in excess being reacted with a strong acid or base. So this is a buffer. Now if we look at 4, same two solutions, but notice how I changed the concentrations. Right, so we still have HF, which is our weak acid. We still have sodium hydroxide, which is a strong base. We come back up here to this equation, and if we look at this, if I have 0.5 molar and I have 1 molar, it's a 1-to-1 reaction, so I'm going to lose 0.5 here, leaving me 0, minus 0.5, plus 0.5, and I don't care about the water that much. So what we have for question number 4 is we have the conjugate base, which is the fluoride ion, but we have a strong base with it because we had excess base. So in this case, this is not going to be a buffer. In order for it to be a buffer, you need to have a weak acid or weak base with its conjugate salt, or you need to have a weak acid or weak base in excess with a strong acid or strong base. All right, so that's figuring out buffers. Now let's do some of the math. And before we get into that, just some general helpful information. So keep in mind that ice tables are going to be fairly helpful for you to do this. You can do an ice table either in concentration, which you want to do for equilibrium or pH purposes, or you can do it in moles and turn that into concentration by dividing by volume. The second thing to keep in mind, almost every reaction we're going to work with is going to be a 1-to-1 reaction, so the stoichiometry should be fairly straightforward. Volumes are additive, so if you're adding a base to an acid, when you're finding the final concentration or final pH, make sure you add together the two volumes to get the final volume of the solution. This one right here, this little piece right here, that volumes are additive. This is the single biggest problem people have when doing these types of calculations. They forget that volumes are additive. divide by the volume of one of the two, and wind up with the wrong answer. And the last thing you should do whenever you're doing a titration question, find equivalence point. Right? A helpful equation that you can use as a derivation of our gas law is to say MAVA equals MBVB. Right? So you're going to be given ways to find 3 of the 4. Find the equivalence volume first. This will help you figure out the total volume of solution at equivalence, which is useful when we have to figure out the pH of certain salt solutions. Right, so let's start off with the different types. We'll start off with some strong. Now, strong acid, strong base pH at the initial portion isn't that bad. You just take the concentration, negative log, and that will give you the pH. At equivalence for a strong acid, strong base, equivalence pH is 7, right? So we know that initial pH is just negative log of initial concentration, and for a base this would be POH. We know that equivalence pH for strong acid, strong base combinations is going to be 7 on the dot. If you're working at any point other than those 2 points, you're going to have to do just some stoichiometry. Right? It's not that difficult of a problem to do. So we have 25 mils of 0.1 molar HCl. We're adding to it 18 mils of 0.8 molar sodium hydroxide. So we'll start by writing out our reaction. We have H plus OH minus yields H2O, and just to be technical. Right, so this is our equation. I'm going to do a quick ice table. I'm going to do the ice table here in moles, because since I'm doing stoichiometry, that's what makes the most sense. Right, so first thing I have to do is I have to figure out how many moles of everything I have. Well, that's pretty straightforward. Right, moles. So moles equals molarity times volume, right, as long as volume's in liter. So molarity, so the number of moles I have of hydrochloric acid is 0.1 molar times 0.025 liters. Or I start off with 0.0025 moles of H+. For my base, again, 0.8 times 0.018 means I'm going to start off with 0.0144 moles of hydroxide. To find my pH, this is a 1-to-1 reaction, so whichever one I have the least amount of is the one that's going to react completely. So minus 0.0025 leaves me no H+. Minus 0.0025 leaves me 0.0119 moles. Right, so my excess here is going to be sodium hydroxide. I'm going to have a basic solution. So I know that POH is negative log of hydroxide concentration. The hydroxide concentration in this case is going to be negative log of 0.0119 moles divided by, now remember, volumes are additive. Right, so the total volume of my solution, so the total volume of the acid and the base is going to be 43 milliliters, or 0.043 liter. Right, so if I plug that in, I get a POH of 0.558, which means that my pH is 14 minus POH, or 13.442. Right, so this is going to be my pH for this particular titration, 13.442. I've added an overabundance of sodium hydroxide. It reacted out all the HCl, and whatever hydroxide is left over will have this fairly high pH. Right, so that's working with strong acid, strong base. If you're working with weak, we're going to break this up into initial pH. We're going to break this up into pH at equivalence and pH after a certain volume has been added. Right, this right here is just our basic Ka problem. So we have a hypochlorous acid solution. Before we start, all we have to do is just do our Ka, right? So hypochlorous acid is HClO. That's going to form H plus and ClO minus. Do our ice table. Start off with 0, both of these. 0.223 minus x. So we have 0.223 minus x, which, because k is really, really small, is going to be about 0.223 plus x plus x. Right, so again, we wind up with Ka is going to be H plus ClO minus over HClO. So we're going to have 3 times 10 to the 8th, or negative 8th, is equal to x squared over 0.223. Just solve for x. Right, so x in this case is going to wind up being 8.18 times 10 to the negative 5th molar. Right, so this again is just our normal Ka problem. And from here, pH is going to be negative log of x, because x is the H plus concentration. And that's going to give us a final pH of 4.09. Right, so we've done a bunch of these to this point, so that calculation really shouldn't be that difficult. Now, our third one is what's going to happen after we've added a little bit of a base to this. So still the same HClO minus. Now we're adding a base, and I gave you an initial volume of HClO minus. Right, so what we want to do here is, again, we probably have an excess of weak acid with some strong base. But we'll just check to find out. All right, so if we take our equation, so HClO minus, or just HClO, sodium hydroxide is OH minus. That'll give us ClO minus plus H2O. Do our ice table. I don't care about water. So that's going to initially be 0. Our initial HClO minus. Now again, because we're doing stoichiometry instead of doing concentration, I'm going to do this in moles. So the number of moles, again, is just 0.223 times 0.030, or 6.69 times 10 to the minus third mole of HClO minus. Our hydroxide is 0.005 times 0.1, or 5 times 10 to the minus fourth moles. Again, hydroxide is going to be our limiting reactant, so we're going to get rid of all of it. So minus 5 times 10 to the minus fourth gives me 0. Minus 5 times 10 to the negative fourth will wind up giving me 6.19 times 10 to the minus third moles. And plus 5 times 10 to the minus fourth gives me 5 times 10 to the minus fourth here. Now, this is interesting, right? If we look at what we have in this solution, we have some number of moles of our weak acid and some number of moles of its conjugate base. So here, what we have is we have a buffer. Right? At every point of a weak, strong titration, up until you hit equivalence, you're going to have a buffer solution. So that means that the math that you're going to do is you're going to take these numbers and you're going to plug them into Henderson-Hasselbalch. And we're going to make this a little bit easier for you as well. Right? Our Henderson-Hasselbalch equation was that pH equals pKa plus log of base concentration over acid concentration. Now the good news is base concentration and acid concentration, since they're both the same solution, the volumes will cancel out. So we can just replace the concentrations with the number of moles. Right? All we need is just the mole ratio of these. So pH equals pKa plus log base over acid. Our pKa, so Ka is 3 times 10 to the minus 8th, which makes our pKa equal to the negative log of that, which our pKa is going to be 7.53. Right, so 7.53 plus log, our base concentration is 5 times 10 to the minus 4th. Our acid concentration is 6.19 times 10 to the minus 3rd. Now, pointing out here, since this is going to be less than 1, the log of our decimal answer is going to be a negative number, which we'll subtract from here, which is the reason why this will actually work out the way that we hope. Right, so we evaluate this, and we actually wind up with a pH of 6.44. Now, the difficult calculation, and it's not really difficult more than it is tedious, is what to do when you hit equivalence. Right, because at equivalence, you don't have a buffer, nor do you have a weak acid in this case. You have to do something a little bit different. So first thing I probably want to do, and again, I'm going to write down this equation, so I'm going to say HClO plus hydroxide. Right, so same reaction, same initial numbers that we were working with before. ClO minus plus H2O. Now, looking at the combination that we have here, we have a weak acid with a strong base. So we would assume that the neutralization pH is going to be basic, right? So at equivalence, we would assume the equivalence pH is going to be greater than 7 because we have weak acid plus strong base. Right, so that's going to be our baseline assumption. It's going to be somewhere above 7. So again, what we'll do is we're given some numbers to work with. We'll do some stoichiometry, so we'll do an ice table. And we'll take it from there. So I have my ice table. As always, I don't care about water. Same HClO minus solution as before. So this is still going to be 6.69 times 10 to the minus 3rd. Now here's the cool thing. Since we know this equation is at equivalence, we know the number of moles that we've added. So we've also added 6.69 times 10 to the minus 3rd moles of this. Right, this is a 1-to-1 reaction. So we're going to be left with no HClO minus, no hydroxide, and our amount of hypochlorite. Okay, so all we've done is we just said, yeah, we're at equivalence. But notice, at equivalence, we have no more acid left over. We have no more pure base left over. All we have is the conjugate base of this. So we don't have a buffer here, which means we can't use Henderson-Hasselbalch to plug this in and make this easy. But what we can do is we know this solution is going to be basic. Since this solution is going to be basic, I need to do a KB. I need to do a base problem. So what I also want Kb for the hypochlorite ion. Right, so Kb of ClO minus. Now we know how to find Kb, right? We know that Ka times Kb equals Kw. So I just solve. So Kw over Ka, 10 to the minus 14th, over 3 times 10 to the minus 8th, and that will give us 3.3 repeating times 10 to the minus 7th. All right, so that's our Kb here. So what we can actually do, and here's the cool thing about this, is we're actually going to reverse this process a tiny little bit. right? Because the thing to remember is that this reaction that we're working with right here is in equilibrium. So we have 8ClO minus. We have our weak base. That weak base is going to react with water to form a tiny little bit of hydroxide and a tiny little bit of HClO. So what we're going to do is we're actually going to do a KB problem with this. Now for this KB problem, so first thing I have to do for it to be a KB problem is I'm going to reverse the direction. Right, so same equation, I'm just reversing the direction. I'm going to have HClO plus OH minus. I'm going to do another ice table. Now, you technically didn't have to do the first ice table. I did the first ice table just to show you that we don't have a buffer in this case, so you can't use the easy way out. What you could do is you could just say, here's how many moles I have, and figure it out that way. Now, the trick with this, though, is because I actually want to do a pH calculation, I don't want to do it, so my original was in moles here, because moles for stoichiometry is a little bit easier. But here, I'm going to be doing a Ka or Kb problem. For Ka or Kb, I would rather be working in concentration. So I know the number of moles, I just have to divide it by the volume. So we need to know how much sodium hydroxide we had to add, right? This is where our MAVA equals MBVB comes in. Right, MA times VA is just the number of moles, so 6.69 times 10 to the minus third equals molarity, which is 0.1 molar, times volume of the base. So volume of the base in this case is going to wind up being 66.9 milliliters. All right, so that's the volume of the base we had to add. If we add to that the volume of the acid, which was 30, we're going to wind up with 96.9 milliliters as our total volume of solution. So here, this number of moles is going to be, and that's going to give us a final molarity of 0.0690 molar. All right, so this is going to be 0.0690 molar. Again, we initially start off with each of these. Remember, Le Chatelier's principle, so we have no product, so the reaction is going to shift to form a tiny little bit of product. So we're going to have minus x, plus x, plus x. Same as always. We can make the same assumption, right? Because if you look at our value of Kb, the value of Kb is significantly smaller than the concentration. So I'm just going to assume that this is 0.069. And now I can just do my Kb problem, right? So 3.3 times 10 to the minus 7th is x squared over 0.069. Okay, so this will give us a value of x equal to 1.51 times 10 to the minus 4th. Since it's a hydroxide, we're going to find our pOH, which is the negative log of this number, or 3.82, which means that the pH of this solution is 10.18. Alright, so that is doing these types of problems. Again, you can make this a little bit easier on yourself if you want. All you really need to do is, again, just do this second ice table right here, figure out what concentration of hypochlorite ion or you're going to have at equivalence using MAVA equals MBVB, and then just do a KB problem because the salt will be basic. Alright, so that's it for some problem solving. Again, if you have questions, feel free to ask, and I will see you guys at some point in the future, I hope.